Hello, Chem 2. Today's lesson is going to be the introductory lesson for the new unit, which is equilibrium. So what we're going to do today is talk about what equilibrium is and what it means. We've seen it a little bit in the last chapter. And then by the end of this particular video, we should be able to write some equilibrium expressions and talk a little bit about what that means and where they came from. So typical administrative items, you have the Chapter 11 exam still on your plate. Will be due on, I think it's the 18th. So there's a little bit of time for you to still get that done. And then what this unit will do is there's two chapters, Chapter 12 and Chapter 13. It'll be split into two parts. So Chapter 12 is first. You have the optional ALs, which are optional, and the required ALs, which are required. And you must get a 75% on the required AL in order to take the test, which will be later on next week. Okay, so let's get to it. So chapter 12 is just called gaseous chemical equilibrium, but we're going to focus a little bit on just chemical equilibrium in general. Your textbook focuses mostly, if not exclusively, on gaseous equilibriums, but we're going to blend together aqueous equilibriums and gaseous, and you'll see what I mean there in a second, but we're looking at two different types of equilibrium. So what is equilibrium? Well, first off, harsh reality, a lot of what you learned in Chem 1 was not true. A lot of reactions, as a matter of fact, probably most reactions, are reversible. And you've heard, you know what the word reversible means. It means it can be flipped inside out or goes two ways. Well, a reversible reaction is a reaction which can, under suitable conditions, go forward and backwards. So you can flip the switch and change the conditions and make it go backwards. For instance, there's a famous reaction of hydrogen reaction with oxygen to make water. That's usually used in fuel cells. You might have seen that if you talked about fuel cells a little bit in Chem 1, where that releases a whole lot of energy when hydrogen and oxygen come together to make water. But under suitable conditions, you can take water and you can add electricity to it. You can add a current through that water, and you can actually split the water into its components of hydrogen and oxygen. That's the hydrolysis. So those two reactions can both happen, the forward and the reverse can both happen, so that particular reaction is a reversible reaction. Well, equilibrium is a special subset of reversible reactions because what happens is the rate of the forward and the rate of the reverse are identical, meaning it goes forward and backwards at the same time. I know that's kind of crazy to understand or appreciate, especially considering a lot of Chem 1, you focused on reactions that would go, you have your reactants and then it creates some type of product. And that was the norm in Chem 1. And you focus a lot on reactants becoming products. Well, the reality is a lot of reactions go from reactants to products. And at the same time, some of the products come together to remake the reactants. Now, how unbalanced that is dependent on the particular reaction. A lot of the reactions we've dealt with so far lie extremely to the right, meaning a whole lot of the reactants come together to make products, but a very, very small amount of the products come together to make reactants. But a tiny, tiny amount does. And some of our reactions that we actually know about that don't appear to not occur are actually ones where the forward reaction is very, very tiny, very insignificant relative to the reverse. So the reverse reaction has essentially already taken place. But when we're at equilibrium, we have a reaction where the forward rate of the reaction is the same as the reverse rate. Graphically, this is what it looks like. You'll see that in a typical reaction where you put two reactants together and allow it to occur, what's going to happen is very, very early on in the reaction, the forward reaction is going to go forward, happen a lot. It's very, very high rate in the forward reaction, mostly because there's a whole lot of reactants right there. The concentration of the reactants are very, very high. And as we saw in the last chapter, as the reaction proceeds and the amount of reactants decrease and decrease and decrease and decrease, the rate at which the reactants become products decreases and decreases and decreases and decreases. At the same time, since this is a reversible reaction, in the beginning, since there are no products, the reverse reaction is essentially at a rate of 0. But as some of the products are present, then a greater and a greater and greater amount of the reverse reactants react and go back to the original reactants until it reaches equilibrium. Right here, where they both have the same rate, is equilibrium. Now, to make sure this is perfectly clear, that does not mean that the concentrations will be the same. The concentrations will not necessarily be the same at equilibrium. The rate at which the change takes place will be the same, but the concentrations will not necessarily be the same for forward and reverse. Way back here at the beginning is a point at which the reactants and products in this graph shows that they are about the same at whatever this time is back here. That just happens to be where the amount of products surpasses the amount of reactants. But it still takes all the way out to here where the rates are the same before there's a lull. There's an appearance that the reaction concentrations are not changing. It appears as actually if the reaction has stopped, and it has not. It has not stopped. It is continuing to go forward and reverse at the same time over and over again. It's called a dynamic equilibrium. It is still reacting, but from the outside looking in, it looks like, it appears as if the products are ever not changing. The amounts are not changing, but they really are. So let's math this up a little bit. We're going to look at what's called a mass action expression. A mass action expression. It's basically a mathematical way to express where the reaction is relative to products and reactants. If I were to go back and look at this initial reaction and look for the product, the ratio of the products to the reactants, and I would look back here in the beginning, the ratio would be very, very large. I'd have it'd be very, very small. I'd have a very small amount of products, look back here, a very small amount of products divided by a very large amount of reactants, and that would be a very, very small expression, of a small value. But sooner or later, I get to a point where the ratio between the products and the reactants, it doesn't necessarily become a magic number per se, but it stays constant, and that's when you reach equilibrium. The point at which the ratio between the products to the reactants does not change. The products to reactants does not change. That is going to point at which you reach equilibrium. So first off, we're going to math this up a little bit. Now, to make this connect very nicely with the last chapter, what we're going to do is focus a little bit on the rate. So if I look at this reaction at the top, and you're going to see a lot of this makeshift reactions of fictitious A plus B becoming C plus D, and the lowercase letters out front are going to be your coefficients. So if the forward reaction and the reverse reaction are happening at the same time, that means a couple things. One, both of them are elementary reactions because they're happening instantaneous. So if they're happening instantaneous, and this is a elementary reaction, let's look at the forward reaction. It's just simply going to be, the rate law is going to be rate of the forward is going to be the K for the forward times the concentration of A raised to its coefficient times the concentration of B raised to its coefficient. So we have A to the M, B to the N. And then if we look at the reverse reaction, it's a little more difficult to look at because we're not used to looking at a reaction backwards. The rate of the reverse reaction, again going backwards, is the rate of the reverse reaction is equal to the K for the reverse reaction times C raised to its coefficient times D raised to its coefficient, C to P, D to Q. Okay, now we said at equilibrium, the two rates are equal. Rate of the forward is equal to rate of the reverse. So what we're going to do is we're going to make these two equations equal to one another. So K forward times A to the M, B to the N is going to be equal to K to the R, C to the P, D to the Q. So we've essentially taken these two rates and set them equal to one another. Okay, one more step. Now what we're going to do is solve for the constant. Now, I already said that for this mass action expression, we're going to look at the mass action expression as being the ratio of products to the reactants. Products to the reactants. And the main reason we do that is based on how aggressive this reaction is, how much it goes to the right or towards the product side, we want to get a bigger and bigger number. So we're going to put products on top and reactants on the bottom. So we're going to solve for K, a K value. K, I guess in this situation, becomes KF over KR. So we're going to take and divide both sides by AMBN and divide both sides by KR, and we get KF over KR equals this expression. This is a mass action expression. This is going to be what's called the equilibrium expression. KF over KR, since KF and KR are both constants, it's going to be a constant value. And what we've done here is we've created what's called the equilibrium expression that will result in the equilibrium constant. So when a system reaches equilibrium, that value of the mass action expression does not change. It is going to stay constant, hence the term equilibrium constant. When the system is at equilibrium, the value that you get from the mass action expression is going to be a constant value called the equilibrium constant. Now, generically, it's called the KEQ. EQ for equilibrium, K for constant. So the KEQ for an aqueous solution, because they're all dissolved in water, is going to be exactly what we saw on the previous slide. Now, this one puts things in a little bit, I consider to be an easier way of looking at things, knowing that the little a, little b, little c, and little d are the coefficients associated with component A, component B, component C, and component D. But your book uses that M, N, P, and Q that was on the previous slide, so I just left that in there. So look what we have here. We have Kc. Kc is the equilibrium constant using, what's the square bracket stand for? That stands for molar concentration. So Kc is the equilibrium constant using the units of concentration, hence the term Kc. It is the equilibrium value that is derived by doing the products of reactants, each of the products raised to its coefficient, each of the reactants raised to its coefficient, but using only concentrations, molar concentrations. Let's look at what this looks like. So here's an expression of the dissociation of, this is actually happens to be acetic acid or vinegar. It breaks into its ions of hydrogens and the acetates. So the equilibrium expression of the Kc expression for this would simply be concentration of hydrogen to the first power times the concentration of acetate to the first power divided by the concentration of acetic acid to the first power. That's whatever value you get from punching the numbers in the concentrations when you are at equilibrium, whatever value you get when you punch those concentrations in at equilibrium, that is going to be your Kc or your equilibrium constant for the dissociation of vinegar. Same thing here, same idea. So ammonium hydroxide dissolving into water to make ammonium and hydroxide. Again, raised to the first, raised to the first, raised to the first, since all the coefficients are 1. Now, this chapter in your book is called gaseous equilibrium, and it focuses on gases. And if you go look at a lot of the examples that show up in your textbook, you're going to see a lot of examples early on using pressures, not using concentrations. But the two can be used interchangeably. They're both KEQ, but the difference is you have a KP versus a Kc. And the Kp, as you might well assume, is because you're doing the exact same expression, the amount of C raised to the little c, the amount of D raised to little d, the amount of A raised to little a, amount of B raised to little b. But all the components, all the pieces, instead of expressing them in concentration, you're going to be expressing them in pressure. Now here's the twist. This is a very, very important twist. The pressures must be in atmospheres. I'm going to repeat that again. The pressures must be in atmospheres because the Kp and the Kc are both unitless expressions. They're just values. So to make sure we get the right number, the right value, we have to make sure we standardize what concentration units we use or what pressure units we use. So we're only going to use for concentration, we're going to use molar concentration, molarity. And for pressure, we're only going to use atmospheres. So that's the two units we're going to use for the two. So get an example. Here's an example of hydrogen gas reacting with iodine gas to produce hydrogen iodide. That is a reversible equilibrium reaction. So the KEQ, or the Kp for the expression, would be pressure HI raised to the second power divided by the pressure of hydrogen to the first power divided by pressure of iodine to the first power. All in pressures, all in atmospheres, you get a value. Now, what if we don't have a homogeneous equilibrium? Well, here's where things become a little fuzzy, and I'm going to be totally honest because your book handles things differently than most textbooks and most colleges will do. So I'm going to talk about what your book does. Essentially, if anything is in gaseous form, you're going to use atmospheres regardless. And if anything's in aqueous form, you're going to molar concentration. That's pretty standard. However, the norm is you don't necessarily have a true heterogeneous equilibrium that has gases and aqueous solutions. That's pretty rare. If that's the case, what you would do is you would have only the ability to have a Kc value. You cannot have a Kp value. The Kp only exists if all of the components are in a gaseous state. All the components of equilibrium are in a gaseous state. If any of them are in aqueous state, the only thing you can use is a Kc, in which case everything, including the gases, would be expressed in concentration. With that being said, your textbook will mix them up. Your textbook is simply looking for, especially the OWL, if you get a heterogeneous equilibrium that has gases and concentrations, aqueous. They want you to take whatever's aqueous and put it into concentration, molar concentration, in the same expression as if there are gases, putting pressures. So that you want to combine them together. But that leaves two particular phases out of the equation. That is solids and liquids. What do we do with those? Well, we ignore them. Actually, we exclude them from the mass action expression. The main reason we do that is the concentration or the pressure. There is no pressure of a solid. There is no pressure of a liquid. There is no pressure of a solid. Those are all materials, but the concentrations of those components will not change over time during the equilibrium process. The concentration will not change if the materials are pure. So since they're not going to show a change, we do not include them in the equilibrium. So simply put, if you see something with a solid or a liquid, you ignore it. You're going to get a value from these expressions. I know this is a lot, but bear with me. You're going to get a value. When you punch all these numbers in, you get a value. If that number is really, really big, I said this earlier, if that number is really, really big, what that means is that the equilibrium, quote unquote, lies to the right, meaning it has a lot of product and a little bit of reactant, has a lot of product and a little bit of reactant. If the equilibrium is very, very small, the KEQ number is small, is very much less than 1, it can't be negative, just a very, very tiny number, then that means the equilibrium lies to the left, meaning there's a very large amount of reactant and a very small amount of product. If you think of the way a reaction normally looks, reactants is on the left, products is on the right. If it lies to the right, it means there's a lot of product. If it lies to the left, it means that when it's done, it has mostly reactants. Okay, last concept is how do we, there's two concepts. One, what's the relationship between Kp and Kc? Well, this is the expression that you can use to express between Kp and Kc. Another way to do this, actually, that I personally think is easier because you don't have to memorize another equation, is to simply change your concentrations into pressure or change your pressures into concentration using the ideal gas law PV equals nRT. N over V, moles over volume, is concentration. So you already have a relationship to go between pressure to concentration, from concentration over to pressure. Now, if you have a gaseous equilibrium, if you have an equilibrium that contains gases, the relationship between Kp is as follows. Kp is equal to Kc, the number, remember this is a unitless expression, the number of Kc. If you multiply it times R, use the atmosphere one since Kp is in atmospheres, times the temperature, use the Kelvin temperature like we always do, raised to the change in the number of moles of gases. And you're going to use the coefficients from the balanced chemical equation. Number of moles on the product side, number of moles on the reactant side. And you're simply going to use the coefficients. So if there were 2 moles on the right-hand side and 4 total moles on the left-hand side, 2 minus 4 would be -2. The delta N would be -2. I always find, like I said, it's easier just to convert my units of C or P back and forth between the two. Now, last concept, manipulating. So the last thing you need to be able to do in this portion, which is sections 1 and 2, talk about how you manipulate your KEQ, whether that be a KP or a KC. How do you manipulate it if you change the appearance of the reaction? So the first manipulation is that if the KEQ of a reaction in the reverse reaction is the inverse. Now this is going to feel very, very, very much like Hess's law. Hess's law, we started manipulating the equations. We would flip them, we'd multiply through by a number, we'd add them up. You're going to do the exact same thing here. However, the rules are completely different. In Hess's law, if you flipped the reaction, you wrote it backwards, the delta H was just the negative. Well, that doesn't make sense here. Okay, let me show you why. So here's an example. If I have H2 plus I2 gives you 2HI, and say the Kc value for that expression was 50, okay? Which means Hi to the second divided by H2 to the first divided by I2 to the first has a value of 50. Suppose I write that equation backwards, okay? I write it backwards, and I want to know what the new Kc is. Well, A, it makes no sense to have a negative because you can't have a negative Kc. Because the only way you have a negative Kc is one of these 3 numbers has to be a negative, and you can't have a negative concentration. So that makes no sense. But how is this different? Well, if I write the expression for this particular equation, okay, I write the Kc expression, we'll call it Kc prime, I get H2 times I2 divided by Hi to the second. Notice what this is relative to this one. It's just upside down, okay? It is essentially the exact same reaction upside down. So if I want to figure out the number, what I got to do is take 1 divided by, take the inverse of 50, and I find that the Kc for this new expression is the inverse of 50, or 0.020. When flipping the reaction, instead of taking the negative of the Kc, you're going to take the inverse of the Kc. It is a little different, but again, it kind of makes sense why using this example. Second possibility of how to manipulate. What if we had to do, remember we had the thing where we had to multiply through by a number. Suppose we multiply through by a number. When we did the Hess's law stuff and we multiplied through by a number, you just multiplied that delta H by that number. That doesn't work, okay? That doesn't work here. Let me show you why. What you're going to do this time is you're going to raise it to the power equal to that number. Again, show you why. Use that exact same equation. There it is. There's that one of the 0.02. Okay, so I have 0.02 is my Kc, and here's my expression that leads to the Kc. Suppose, again, I want to multiply through by 2. I took my 2 times 2 is 4, 1 times 2 is 2, 1 times 2 is 2, and I rewrote that entire equation, but I multiplied everything through by 2. So what's my new Kc going to be? Well, again, a way to see what you're going to do or why you're going to do it, let's write the expression for this equation. Kc for this second new equation is K2 to the second, I2 to the second, Hi to the fourth, which can be more interestingly written as H2 I2 over H2 to the second, all squared. See where that 2 came from? That's that number we multiplied through by. So in order to determine the concentration, or sorry, the rate law constant, blah, the equilibrium constant of this new reaction, we're just going to take the old equilibrium constant and raise it to the second power, and we get this new number. Okay, again, these numbers are unitless, have no units, it's just a value. So we want to make sure that we do everything on the up and up, but in order to manipulate this, since we're multiplying through by a number, we're going to raise that number. What if we divide by a number? Okay, So suppose what I've done here is I've divided all my coefficients by 2. I've divided all my coefficients by 2. So I divided by 2 here. 1 divided by 2 is a half. 1 divided by 2 is a half. And I have my new Kc. And I want to get my equilibrium constant value for this. Well, I divided by 2. That is the same as raising to the 1/2 power, or that's, if I divide by 2, that is the same as multiplying times 1/2. So what I'm going to do is I'm going to take my equilibrium constant, and since that is the same as raising it to the 1/2 power, I'm going to take my old equilibrium constant and raise it to 1/2 power, which is the same as taking the square root, and I get 0.14. Okay, so whatever you do to the coefficients, whatever you multiply through by, that's going to be the number that you're going to raise the power to. Raise it to that power. Multiply through by a half, raise it to a half. Multiply through by 2, raise it to a second. Okay, last manipulation. This is getting a little long video. I apologize, but we are covering 2 sections in today's discussion. Last thing is the adding. Okay, the last thing you can do in Hess's law, one was to flip it, one was to multiply through by a number, the last thing you could do was add it. Well, in this case, the KEQ for a net reaction, one is made up of adding together multiple reactions, is going to be equal to, instead of the sum of the delta H's, it's going to be equal to the product of the delta of the KEQs. Let me show you how or why that works. So I'm going to do it generically because it makes it a little bit cleaner without having a bunch of actual compounds. A plus B equals C, say that has a value of 0.5. A plus C equals D, that gives you 0.2. Again, picking just numbers to show you how this works. Let's put them together, and you get 2 A's plus a B. C's cancel out, okay, giving you D. And I want to go ahead and I want to figure out what that K expression is, what's the equilibrium constant expression for that last reaction, which was the sum of 2 other reactions. So let's put them together. So here's my K1, here's my K2, here's my KT. How are these 3 numbers, how are these 3 expressions related to one another? Well, if you were paying attention to last video, in the last slide, we talked about, it said that the KEQ for the total would be equal to the product of the KEQs, the other ones. Let's look at this. If I take the first expression times the second expression, and I cancel out my C's, I get my third expression. So that means my K1 times my K2 is going to be equal to my KT. So my K1, which was 0.5, my K2 is 0.2. I multiply them together, I get 0.1 is my KEQ for my last expression. Okay, so let's see if you kind of get how to do the manipulations. Put it all together. Here are 3 reactions. I got reaction number 1, which I gave you a K value for. Reaction number 2, I gave you a K value for. And reaction number 3, which is what I want to know what the K value is based on the other 2. Go ahead and pause the video for a bit. See if you can manipulate those 3 reactions very, very much like you did for Hess's law, remembering the change in rules. Instead, when you flip a reaction, instead of taking the negative of it, you're going to take the inverse. Whenever you multiply through by a number, instead of multiplying that delta H, you're going to take the KT and raise it to that power. And when you add the reactions together, instead of adding the K's together, you're going to multiply them together. So pause the video, try this one on your own, and then when you restart the video, I'll show you how to do this problem. Okay, let's see how you did. So first thing I do is I look for different key points, just like we did in the Hess's law. So I noticed that there's 4 coppers there, and there's 2 coppers there in my final. The coppers are only in one spot. They're on the correct side, but they have the wrong coefficient. So if I take that first reaction and I rewrite it, but multiply through by 1/2, I'm going to get a new reaction. So I take that first reaction and I multiply through by 1/2, and I get this bottom reaction. And since I've multiplied through by 1/2, I'm going to raise my first KT, my 0.012, to the 1/2 power, or take the square root of that number, and I get 0.11. Then what I'm going to do is look for other points. Well, Oxygens are all over the place. So I'm going to look at the copper. The copper oxide is here, and the copper oxide is there. So my copper oxide are on both sides of the reaction. They have the right coefficient, but it's backwards. So since it's in the right spot, has the right coefficient, I don't have to multiply through by anything, but I do have to flip it. So what I'm going to do in order to flip it is I'm going to flip it around 100, backwards, which means I need to take the inverse of the second K2. So 1 divided by 4.2 is 0.24. Kind of an ironic twist of the use of numbers. The inverse of 4.2 is 0.24. Okay, so since these two reactions add up to give me the overall reaction, notice that the Cu2O cancels on both sides. 2 coppers, half an oxygen plus half an oxygen gives you a whole oxygen, 2 CuOs. So these add up to give you those. Then what I need to do is have to multiply these two numbers together to get my overall equation and overall number, and it's 0.026. Okay, so that's the first two sections. It's all about the manipulating of the variables, what to do, what the heck a KEQ expression is, what does it mean. What we're going to do next is we're going to actually start using the K expression. That is where the money is in this particular unit, where you get a chance to actually use the K and see what that means, and that's where basically all the work is, all the magic happens with the K expression. So we're going to do that with the next section. Hopefully everybody's staying healthy and safe. I look forward to seeing you sometime. Seems like it won't be this year, but feel free to pop in next year when school year does start and say, hey, in the meantime, you can always see my smiling face. And maybe if you decide to take advantage of the camera, we can see your smiling face in the text, in the chats, team chats on Tuesdays and Thursdays. Take care, toodles, and I will see you on the next video. And always remember, never forget, and you know it, this phrase that pays, sig figs really do matter. Toodles.